Antennas and Propagation Chapter, IEEE Kerala section, and is also the Vice Chairman, IEEE Antennas and Propagation Chapter, IEEE Kerala section from 2016 to 2017. May I request Dr. Chinmoy Saha to come on stage.
So I'll be talking on some of our recent work. Which we have started a couple of years before on antennas for terahertz applications. So the major part of this talk will be based on our work on photoconductive antennas for terahertz applications. So this is my institute. As you have seen already, this is the panoramic view of IIST, which is not very far, around 300 kilometers from here, at the southern part of Kerala. And Professor Dr. Abdul Kalam was the pioneer of this particular institute. It is basically his brainchild. And the uniqueness of our institute is, unlike other IITs and NITs, our focus is more towards space, and of course with other things as well. So I'll be talking on some challenges initially, and then I'll be going to various applications, and then we'll be talking on the different choices for antenna design, especially the material choices and some of the realizations. It's not a very straightforward field. As you'll see during my presentation, you need inputs from other branches of engineering, especially the photonics and material science as well. And then I'll be showing you some of the PCAs which we have realized and successfully tested with the collaboration with Space Application Center Ahmedabad and ISER Trivandrum. So this is, it's a very well-known slide, that the spectrum over the horizon, and as we know that this particular region, which is we call the terahertz gap, is relatively unexplored, and it might have certain applications. It has many advantages, as you can see, but due to unavailability of proper laboratory generated sources, this is really unexplored, and this particular research field has been mainly initiated by few groups. One of the strongest group is the NASA under the leadership of Dr. Gautam Chattopadhyay, and there are few other European groups also. And truly speaking, as you know, in India, the research on terahertz, only it's happening on a few pockets. One of the pockets is TIFR, Tata Institute of Fundamental Research with Professor Prabhu, and we have started this particular work a few years before, and we faced many challenges. So I'll be telling some of the stories and how we have been benefited due to the collaboration with the CRNN University of Calcutta and the Space Application Center, Ahmedabad. So these are the challenges I was talking about. These are the facts. The wavelength is in the order of micron. So this is not like your conventional fabrication. You have to rely on the VLSI technologies. You need to have the nanofabrication facilities, that is clean room and so on, to come up with any device or antennas when you think of above 100 gigahertz, because your wavelength is going into the region of micron. And to get a feel of what it actually terahertz is with respect to the classical physics, it is the photonic devices also, that is because the injection of photons create the carriers, so you need to see what's the temperature associated with that. So if you write H nu is equal to kVt, then that gives you the temperature, which is 40 Kelvin, and that's why physicists call that terahertz is a cool phenomenon. And other main issue is the atmospheric absorption, especially due to the presence of water vapor and so on. By a very simple calculation, you can show a terahertz signal in open atmosphere cannot even travel few meters. It gets highly attenuated, and that's very visible from this particular attenuation over frequency plot. Okay, so this is more on that. As you can see, that as you go above 100 gigahertz, it is a severe attenuation, and that's one of the challenges. And that's why terahertz cannot replace the conventional terrestrial communication, and it cannot act as a long distance communication link, but it can work in certain environments, especially you don't have the effect of the atmosphere, or you can use it for some kind of indoor applications, very short range application, because it has tremendous potential. Within few seconds, you can transfer a lot of data, and you can basically establish a short range but extremely high speed communication link for several kind of indoor applications. Otherwise, you can use for, of course, the space applications. And this is when the terahertz antenna and the terahertz research was booming in over last few decades. This sort was projected in one of the IEEE transactions on terahertz science and technology. It's a futuristic projection till 2020, and this shows that this particular arena of research is going to grow exponentially, and due to various demands, not only for consumer aspects, but also for some security applications and other upcoming applications. As I mentioned, that the main difference of doing research in this particular area, especially in this particular crowd, most of the researchers are from the microwave circuits and antennas, but we typically work in the lower design of spectrums, and we are basically doing the conventional microwaves. But when we go to the higher side of the spectrum, it's just not the conventional concepts of antenna engineering or microwave engineering. You need to have control, and you need to have collaborations and support from your nanoelectronics group, because your fabrication will be mostly based on your clean room facilities. And also, as I'll be showing you during my discussion of the photoconductive antennas, you need to have a clear understanding also facilities on the photonics, and a choice of the materials is extremely crucial. So it is indeed a kind of interdisciplinary kind of research, where it's not a ball game of one or two groups, but multiple groups with multiple expertise, experimental facilities, and so on, must join hands together to come up with this particular research solution. So, being part of the Department of Space, and ISRO slowly planning to going to the higher side of the spectrum, our institute also made us some kind of plan, short term as well as long term plan, and we are trying to establish facilities initially up to 325 gigahertz, and then we have a further plan, futuristic plan to go to the higher side of the spectrum, maybe up to 1.21 terahertz. The main challenge is it is extremely costly. It is extremely costly because the characterization facility and the clean room facility, running a clean room in an academic campus, is not that easy. So considering all these aspects and the cost involved, we are trying to slowly, move towards the higher side of the spectrum. And currently we are doing some work up to 400 gigahertz, and later on, based on the facilities and the funds, will be going to the higher side of the spectrum. Now, when we think of the terahertz sources, what does the physics say? The physics says any thermal radiation can fall into the region of terahertz radiation, because you can do the calculation and you can see the cold objects such as 10 to 100 Kelvin, their radiation, according to the black body radiation rule, it will be falling into the region of terahertz. And this particular graph, as you know, it comes from the classical physics. This particular region is basically the Rayleigh-Jeans law, as you will be knowing into the initial studies of the quantum mechanics, and this is the Planck's distribution. And this says that there might be different kind of natural sources of radiation which falls in the terahertz design, but those are not useful because these are not focused, these are not properly directed, and that's why those can be of good interest for physicists but not for the engineers, because it won't have any application until and unless we can come up with proper sources with high directivity and other features that I will be coming to. So this shows you, output power versus frequency plot for some of the semiconductor-based devices, also from the photonics and optical side. And as you can see, that we have well-known semiconductor-based devices like gallium arsenide-based, or the IMPAT, or the GaN, and so on and so forth. Into the lower side of the spectrum, similarly, the laser-based, like the QCL, the quantum cascade laser, and the 3-5 semiconductor lasers, and all these things are there in the higher side of the spectrum. So the lower side of the spectrum is dominated by microwave people. In the higher side of the spectrum, we have the well-established sources contributed by the optical group and mainly the physics people, but in between we have a gap which we call the terahertz gap, and different concepts like GHG, parametric amplifier, and all these things, different frequency generation, people have tried to come up with this thing to come to to get the terahertz signal. So how can we fill up that gap, produce the terahertz signal? So this is the gap we are trying to get. This is one of the techniques. You try to move toward the higher side of the spectrum. You have the solid state sources, and by some mechanisms, maybe frequency multiplier or something like that, we can do up conversion. Otherwise, you try to get a difference frequency generation, like a bit generation, when you have two frequencies, omega 1 and omega 2, and you get omega 1 minus omega 2. So that is the down conversion concept. These are the basic principles for both the techniques. Under the frequency down conversion, we have a technique which is called optical rectification, where you have a femtosecond laser pulse which gets incident on a nonlinear crystal. I'll be coming into a little bit more on that. And then, using the difference frequency generation concept, you can produce the difference of two optical laser pulses, that is omega 1 and omega 2. By choosing the proper values of omega 1 and omega 2, you can come up with a frequency which will be falling into the terahertz region. So this, as I mentioned, is optical rectification and the difference frequency generation are the two major techniques that can be used. So in this particular one, you have a femtosecond laser pulse which falls on a nonlinear medium which has a second order nonlinear susceptibility, and you can get terahertz signal by apply very simple mathematics starting from Maxwell's law. You can show that if you have a second order time derivative of your polarization, then you can have the radiation. But most of these dielectrics and most of the materials are linear, so you don't get the second order dielectric materials having the second order susceptibility. So you need to get proper crystals or proper medium to excite that particular phenomenon. So this is a bit of more theoretical explanation. If you have an incident field like this in the phasor form, E naught e to the power j omega t, then you can get I mean, here the polarization is not the linearly proportional to the electric field, but it is square of the electric field. So you get this term, as you can see from this particular equation. If you have a Gaussian pulse, sinusoidally modulated Gaussian pulse, e to the power minus alpha t square, and then the sinusoidal part in phasor e to the power minus j omega t, then you in fact get this second order polarization which is like this, whose second derivative will also be Gaussian. That's why with this beam as the incident pulse, you get this type of pulse which you can, with proper choice of the materials, you can produce this particular terahertz beam. As I mentioned, the other technique is you have two frequencies which are omega 1 and omega 2 respectively, and you get a difference frequency from that, because this particular this is the general expression for the polarization, and this is the second order term which is most prevalent in this particular case. So you have two beams of two frequencies with omega 1 and omega 2, and you make them incident on that type of crystal having that type of phenomenon. In fact, you get a lot of terms which has some of the undesired terms also, but you get the difference frequency generation GFG. So the first term is like your optical rectification, then you have harmonics of the two sources which will be going further in the optical region, because your goal is to produce omega 1 minus omega 2. So using the optical, you are trying to coming down to the terahertz. So you are not interested with the second or third term, but you are interested with the fourth term, because that's what you are aiming for, omega 1 minus omega 2. And the last one is also will be going into the higher side of the spectrum. Other technique, the frequency multipliers. This was demonstrated by the NASA group, by Gautam Chattopadhyay and all. So that is basically a frequency multiplication concept by using cascaded multipliers of several amplification factors 3 and 2 and so on. They have shown that using a solid state source or even a conventional source of 8.8 gigahertz, you can come up with 1.7 gigahertz. It has certain limitations and drawbacks, because as you know, you cannot just keep on increasing the number of multipliers, and you cannot just get any conversion factors, because you have to take care of your phase noise and efficiency. So that's why this can be probably useful up to certain side of the spectrum, but then you have to have other process. So that one of the other techniques on which we have attempted and we have done a bit of progress is the photoconductive antenna. And the basic principle is quite simple. You have a semiconductor substrate, not a conventional dielectric substrate. It's a semiconductor substrate. So here, the choice of that one of the two parameters of importance are the electron mobility and the minority carrier lifetime. Normally, the antenna engineers never thinks of these parameters, but here the carrier generation is based on the photon to electron conversion. So you need to concentrate more on these two parameters. So basic fact is like this: you have a femtosecond laser pulse which gets incident on the that is basically kind of dipole structure. We call it terahertz dipole. So there you shine the semiconductor laser with that particular femtosecond laser pulse, which creates your transient carriers by conversion from photon to electrons. and then on the other side you get the terahertz signal. So here the minority carrier lifetime and the carrier mobility is of must importance, and this gap you call this terahertz gap, so you should have a proper focusing mechanism because this gap is just of the order of few microns and around 10 microns and so on. That's why the experiment as well as fabrication is so difficult. This is the, for the beginners, this is the basic concept and explanation. So you have the femtosecond laser pulse shining on the semiconductor, you get the carriers, and that establishes the transient current and that gives you the terahertz beams. Even by, if you go a little bit of more literature, you can show, even though you are talking about the photoconductive antennas or terahertz antennas, whatever it is, the fundamental antenna concepts remain same. So if you use some of the field concepts of known antennas like the dipole antennas and your loop antennas, you know that for Hertzian dipole or any kind of dipole antennas, normally you have the theta component of your electric field and phi component of the magnetic field. Using the semiconductor transport equation and the continuity equation, you can show similar kind of, identical kind of expression that here also the ETH, that is the electric field associated with a radiated terahertz beam, which is by the process as I mentioned, is having the same theta component and it is proportional to the photocurrent. That's why the transient current is so important. Okay, so these are some of the specifications we initially thought of starting. We faced a lot of challenges because the type of semiconductor that we did our theoretical studies and we thought it will be available with us, ultimately we couldn't get that, but we got something closer with that itself. We did our experiment. I'll be coming to that particular part. So these are some of the material choices for that, but you know the silicon will not be of much use because of it has low breakdown voltage and slow switching speed. So we will probably think of some compound semiconductors. So gallium arsenide is of course a good choice, as you know, because it's a direct bandgap semiconductor, its electric field breakdown field is higher, moreover it has a very high electron mobility, low dark current, so that it will not be unnecessarily illuminated by the background noise, and more importantly it has very short carrier lifetime, and low temperature grown gallium arsenide is even a better choice than conventional gallium arsenide. So these are some of the substrate choices I mentioned, and normally the Ti-gold, that is the titanium and gold alloy is, and some people are even thinking of graphene are good choices as far as the metallization part is concerned, and the shapes, different known antenna shapes have been attempted if you just dig through the literature of the terahertz antennas. So before we went for our specification and we went for what type of structure we want to fabricate, we did some theoretical studies. So these are some of those observations from one of my MTech students. That is how the photocurrent changes with respect to the bias voltage, with respect to the the intensity of the optical beam, and also the photoconductive gap. And these are quite well expected results, because as you will be increasing the bias voltage, you should get more photocurrent provided your device is in the linear region. With more optical beam power level, of course the carrier generation will be more, and that's why you get a more photocurrent, and the other case of photoconductive gap is also exciting. One of the difference with this PCA and the conventional antennas is the the overall efficiency. Now, for the antenna design, we are normally concerned with the radiation efficiency. But here, the overall efficiency is not just dominated by the radiation efficiency, but by other two factors. More important, which one is the illumination efficiency. That is basically how good your material is in converting photons into electrons. That we call eta LE, and eta M is the matching efficiency. So these three together gives rise to the combined efficiency of your photoconductive antennas. And considering this particular aspect that you know you are having a semiconductor substrate, and then once the beam, terahertz beam leaves the substrate, is going to the air, and obviously it will be having the refraction effect, and the beam will be diverging as it's going to the Snell's law, right? You need to collimate the beam. We can have some kind of lenses to collimate the beam, and we used this kind of commercial lenses which you can get from some of the manufacturers. These are basically some silicon lenses, by one of the, we purchased this lens from one of the manufacturers, which is German based, from Bangkok, and the basic purpose is basically to collimate the beam, and thereby you try to get more gain. So these are some of the very initial studies with dipole and silicon lens together, and the simulation also you have to do with proper care, because otherwise you will be ending up with various kind of spurious results. And one of the things that is also concerned is you need the current to be concentrated into the dipole region, not into the bias lines, because you are having a DC bias to excite the current. So one of the things we thought of to reduce this unwanted current that is coming back to the your DC source region, that the conventional concept of some kind of isolators we applied, which is basically some kind of EBG type of structures, and then we tried to enhance the gain. So this is one of the representative plots, and as you can see, we are getting only a 7.29 dBi of gain with even after putting those isolating structures and so on. So this is some kind of surface current distribution we can without those structures, and then we are attempting to enhance the gain by some mechanisms. So I will show some of the very recent work in this particular thing. So we have a photoconductive antenna. This part I have already discussed. We have a DC bias and we have the femtosecond laser pulse, and then you get that terahertz beam from here. And then we used as kind of gallium arsenide horn on the photoconductive antenna, which is then followed by the silicon lens, and that gives quite good gain even with a single photoconductive antenna. And moreover, when you back this antenna with a gold mirror on the back side, you get rid of much of the back radiation which is coming, and thereby you enhance the gain further. I have already talked on this particular thing, and these are the initial antenna that we considered. So this is the PCA part, which is like basically a PCA dipole. Then you have these design parameters for this particular antenna, and then this is the part I was talking about. You have a gallium arsenide horn which is embedded on the antenna, and then you put the silicon lens for enhancing the gain further. And then the last part is a bit of animation involved here. So this is the antenna which sits here. You have the horn and the lens, and then you put this gold mirror, okay, with proper physics and proper design. You put it at a distance of λ/4, so that the back reflected signal will be having a λ/2, which corresponds to 180 degree. Another 180 degree you get due to the metallic reflection, so that the back radiation and the forward radiation is in sync, and thereby you enhance the gain. So this is the composite 3D structures. And with this, as you can see, you get a 0.8 terahertz, at 0.8 terahertz you get a kind of good matching, and the maximum gain after incorporating all these structures we could get was around 25 dBi, and with some of the structures it was around 27 dBi. So this 27 dBi. So with the final 3D gain pattern with and without the mirror, as you can see, by placing the mirror, the right side one, you make your beam further focused, and the maximum gain is 27.3 dBi. So this is the some current distribution with and without the mirror. So it's a comparative look. You have the standalone dipole that gives only 4 dBi, then you put it to the silicon lens, you enhance the gain, further you enhance by putting the gallium arsenide horn, and then you put a horn and silicon lens. Now it's quite good, but it is the best that we got was with this configuration with mirror, and these were still not fabricated because of the challenges involved. We published our initial results in APS San Diego 2017. So this realization part, we had to rely on our big brother space application center Ahmedabad. So these are some process flows involved in the clean room and realization of this kind of PCS. This type of infrastructures, your EV lithography and different kind of dicing, slicing, and all this. Typically, the VLSI people are more equipped with this thing. As of now, our institute doesn't have any clean room, but it is in the process. We will be having our own clean room, and we can do all these things in our campus itself. So these are some of the realized structures. Of course, the zoom view, one bow tie shaped and the fractal bow tie shaped kind of antennas. The initial characterization, that is the DC characterization, and this is some of the initial results that we got around 400 terahertz and so on. We get those results. So this is just a journey started in this particular region. I must acknowledge the people who have supported in this journey. Professor Siddiqui present here and his colleagues at CRN in Kolkata, Professor Prabhu, Dr. Gautam Chattopadhyay and Rajiv Kini, he was the person who was helping us in the characterization in his lab in ISAT Trivandrum. So with this I conclude my talk. These are some students who have worked in various projects, and this is just a kind of announcement or invitation that our section, Kerala section, is hosting this prestigious conference, TenCon, at Grand Hyatt Kochi 17 to 20 October 2019. The regular submission is already over. We have got 1200 submissions, but there are 2 special sessions which is being supported by GRSS and APS Society. So you are welcome to submit papers in these 2 special sessions, which is open till 31st of June. So in this, I conclude the talk. Thank you very much. We would like to thank Professor Chinmoy for his enlightening lecture. I would request Dr. In Bhaskar to come up on the dais and present moment to Professor Chinmoy sir.
Thank you, sir.